So use the left pointer, right pointer. So start here, and is equals to this. So it's bigger than the target, which is what we want is 9. So the thing is this is too big. So the first thing do is the next number for this is increasing. So I'll say that this is increase, right? And then if we move over here, it's sort of like decrease. So the question asking is that do we want to go down or we want to go up? So definitely we want to go down, right? So if we want to go down, we move the right pointer, go to here. So now we have this 8. So do we want to go up or down? We want to go up. So up, basically if you want to go up, logically speaking, this is the trajectory for you wanting to go up. But for here is for the trajectory if you want to go down. Then you move the right pointer. So I want to go up. I move over here. So right now is this value, because it's this is this, and now this value I want to go down. This belongs to here. Come over here, get this. So this is this, and do we want to go up or down? We want to go up. We take these routes, and then this equals to this, which is the final this. So there you have it. You have the answer. Also, there's the brute force way of doing things. So the first item is definitely this. So this and this. So this is not equal to this. And we know that it's a sort of like ascending order per se. So if we want to increase value, we keep it. We actually do like a adjacent value, run throughout the whole values. So this, not this. This, not this. This, not this. This, exceed. So right now, we're saying that this is up of this, which is not good. And if we were to, because any trajectory that you move towards here, it's always this, right? So if this already is this, so if it's already up, there's no way you want to up it even more, because anything that goes here is always up, right? So if this is already up, there's no way you want to up it even more. So it's like kind of like saying that there's no point for this set to continue moving towards the right. So it automatically cancels out for this case. For just specifically for talking about this case, that there's no need for it to continue moving towards the right. We're not talking about this, we're not talking about this, we're just talking specifically about this, right? Because for this, for it to, we want to get this. And if it's already up for this, there's no need for me to keep on moving, because moving forward will be even worse, will up even more. And that's not what we want. So like we move on to talk about this number per se. So it's like trying out for this, and then this, and then this, and then this. It just explains a repeat per se. So for this, we start off again. So it's up whenever it keeps on going. We start with this, go with this, this now equals to this now equal to this, this. It becomes up again. So this is up. And like what we discussed earlier is that if you could keep on moving over here, it will just keep on up. And for specifically for this case, there's no need for me to actually look at orders, right? Because if you go there, it's this, it's up. And for over here, this case already, it's already up already. And if we keep on moving over here, it's even gonna up even more, which is even worse. So now we look at this, and look at this, and straight away we get this. We sort of like found the answer. So therefore it's equals to this, because it's this and this. So it then becomes like the indices 3, 4. Then we actually go on to actually discuss about like the worst case time complexity. It's because that it started off with the first value, and then the possibility of you going to the rest of the value. And one argument is like saying that like if we reach until this stage, why don't we check about this? If you were to see, it's sort of like a repetition for the value. So say for example this and this, right? For this value, if we were to check for him, we always go by the first and going by the following. And if you see, there's sort of like a collision between this and this as well. So the first set and the second set, it's already colliding, and there's no need for me to actually go backwards, because it's been covered by the first sets. And I just believe that whatever combination that involves like 1, it's all like covered at the first sets. So there's no need for me to bother about set for 1 and set for 3, because for say like set 3, similarly it has run through here, 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 and here, right? So for this value, it doesn't actually need to go back to check with 3 sets, because 3 sets already covered every single thing, and 1 set has covered every single thing. It has covered over here. So for the 3 sets, it has covered the whole entirety area of this area per se. So if you were to keep on moving forward, you don't really need to care about the interaction for the front values. For 1, for 3, you don't need to care. So let's just say that we run till quite deep into the equation, right? So we come over here and then we kind of like bothered. Have you checked with here already, per se? But when we trace backwards, was that during the fourth set, it already started going here, and if you were to see that there is actually a collision between this set and this set. So at the fourth set, he already has covered this collision. And when you are at the number 7, you kind of like worried about the behind set for some reason, and then let's just say you are very worried about the fourth set. But then you look at the fourth set, which actually happened previously, it actually has already covered for it already. So the fourth set is checking for here, for here, for here, for here, which includes the one that you are worried about, the 7th one. So so I think it kind of like become the big O of n square is because for say set 1, we check all this, right? And maybe for set 3, it might be set 4, check this, right? So it's like and so it's like a lot of n's, right? So there's like a total of like, I don't know, 8 n's. So usually it would automatically be referred as like n squared per se, because the number of elements here is like 1, 2, 3, 4, 5, 6, 7. It's like n is equals to 7, right? So it's like if it's 8n, it's basically n times n, right? Which is also equals to n squared. Because this value is already like sort of already a n. Therefore, big O of n squared for the time complexity for this. So yep, everything comes to an end.